Welcome back to physical chemistry. Today we're going to go up in energy and talk about what happens if we put more energy into our system than the bonds can handle. So if we put a lot of energy into our system, most of it will go into core electrons because they can absorb more energy. If we take this case, we're looking at a Bohr atomic model, so this is the whole second shell. It's a lot easier to draw it this way. It's not obviously a quantum mechanical model. If we have enough energy, so we have an X-ray or an electron, some way of dumping in a lot of energy, we can knock out electrons from these core energy levels. We will also knock out bonding electrons, which will cause our materials to break. But for the purposes of spectroscopy, for our purposes of actually measuring something useful, it is the core electrons that are more interesting. So this, our first example, would be called X-ray photoelectron spectroscopy, in which an X-ray coming in excites some kind of core electron and shoots it out. The electron comes out with a kinetic energy that is equal to the energy of the X-ray minus the energy that's required to get the electron from here to the vacuum state, to outside the molecule or atom, whatever it is. That is mostly made up of the energy of this electron. And so we can measure the kinetic energy of the electron, subtract the energy of the X-ray, very much like we would have done with Raman, to get a shift, to get the energy difference, and that tells us what the energy of the binding energy of this electron is. This technique comes with a few practical difficulties. The first practical difficulty is our X-ray needs to be one color, and X-rays typically aren't one color, so that becomes fairly expensive to filter out all of the other X-rays that we don't want, because X-rays pass through lots of things. It's not very absorbent. That's good because it means our penetration will be good, but our our color is not very sharp. Typically we would do this using a bent crystal of something which will behave like a grating, behave like a diffraction grating. The lines of atoms in our crystal will behave like a diffraction grating, and they will split the X-ray into different colors. And in the reflected spectrum, all of the electrons, in the reflected spectrum, the only X-rays that come off will be the ones that we want, a relatively narrow band. There's a second problem. The second problem is these electrons, we have to measure their kinetic energy before they hit anything else, otherwise they won't have the same energy. That means that one, our depth of measurement is not very high, caused by the electrons escaping. Not the X-rays going in, they can go straight through our sample, but caused by the electrons escaping, we will not be able to measure very deep inside our sample, which is a good and a bad thing. The other thing is we need a vacuum, otherwise this electron is going to hit some air on the way to our detector, so our measurement will have to be done in a vacuum. In the next possibility, we can shoot out a core electron, leaving a hole in the first step, and look at what happens next, which gives us a next technique. In a second step, an electron from a higher level drops into this hole, giving out a photon. This photon is also an X-ray, but it's not as high energy as the one we had before, and it behaves exactly like fluorescence. We're putting in high energy, shooting this one out, getting out lower energy, and so this technique is called X-ray fluorescence. It is also an excellent technique because we don't need a vacuum. We've got an X-ray coming in, got an X-ray coming out, so we can also penetrate relatively deeply inside our sample, although this X-ray is not that high energy, and so it won't penetrate so far, so it'll be limited, but it's way better. This technique is often used to check purity of metals, for example, because you can easily shine an X-ray in, measure the X-ray, it's quick, you can do it in air, so you can come up with a box. Obviously you don't want the X-rays to escape, but you can hold it up against your sample and measure it, so you don't need to even take it with you. There is a second advantage of this same technique, which is that the X-ray coming out is not charged and has no information on the energy of the thing that we put in to start with. So it doesn't matter what energy we put in, we get the same X-ray out because it's just the difference in energy between these two internal levels. That means that if our sample charges up, because we've shot electrons out, it doesn't change the energy of this X-ray, whereas if we had an electron coming out, it would hold it back or accelerate it. It also means that we don't need a single color of X-rays to give this one out, or in our electron microscope, for example, we don't need a tight energy supply of electrons to be able to measure it, and because we're measuring a photon and not an electron, our electrons that we shoot in won't cause us a major problem. If we try to shoot in an electron and measure an electron coming out, we have a very large technical problem of how do we work out which electrons are the right ones. Because this particular technique measures the difference in energy between two core energy levels, it tells us very quickly which element we're talking about. Why is that interesting? Well, the one that we had before, X-ray photoelectron spectroscopy, where we measure the energy of the electron that comes out. If we bond these electrons, the outside ones, to something else, that will change the level of the core electrons as well. They will be shifted slightly, and so we will get an energy shift. And because we could have a lot of elements in there, like infrared, it is best if we know a lot about our sample before we start. If we don't know what's in there, it can become very difficult because all of our bands are shifting depending on what they're attached to. If we know what it is, then it tells us more information. In this case, we have an advantage and a disadvantage at the same time. The advantage and disadvantage is because it's an internal level, we don't see that because they tend to shift together, so it's a lot smaller. It becomes more difficult to measure. But if we find something lying around, or we get given a sample by a company to measure, or we're doing forensic analysis and it's something that was found at a crime scene, we don't know what it is to start with, this is an excellent technique to start with because it tells us what elements are in our sample. There is an obvious problem. The obvious problem is because it's a core energy transfer, very light elements can't do it. Hydrogen, for example, is invisible because if we shoot one electron out, it doesn't have any, so it can't do it. If we have lithium, it's also invisible because it doesn't have any inner electrons. So we need several energy levels to do it, and the heavier the atom is, the more likely we are to see this. In yet another type, or yet another possibility, instead of giving out a photon, an X-ray, when dropping in, it can donate that energy to another electron, which will come out of our core of our atom, and that is an Auger electron. In this case, 3 electrons are involved, and so once again we get more information about the energy levels and the bonding. And on the other hand, it is then suddenly affected by charge again, but we do have the advantage that the energy of our source doesn't have to be as tight as before with XPS, because the shooting out, the hole is in a defined position, so these energy transformations are all internal, and that means that this energy is quite fixed. The probability that we get an Auger electron out or an X-ray photon is dependent on the mass of the element that we have, and so we will prefer one technique or the other depending on whether we expect heavy elements or light elements. But Ogee is a specialized technique because we need to measure the energy of these electrons, so it's not in vacuum, so therefore it's less exciting or less general. No, it's less generally used than X-ray fluorescence. So here I've written a table of the properties, or some of the properties of these things, the ones that sprang to mind. So if we take the first one, it's do we need a vacuum? We need a vacuum for XPS because we need to measure accurately the energy of the electron coming out, and it obviously will interfere with it if it hits things on the way. We don't need one for X-ray fluorescence because an X-ray goes in and an X-ray comes out. We need it for the other two techniques because here we have an electron coming in. EDX is when we shoot in an electron and we get an X-ray out. And for Auger, we're shooting an electron in and getting an electron out. It's particularly important because the low energy electron that comes out is very easy to lose. So in these two cases, the vacuum is critically important. In this case, it is quite important, and in this case, we don't need it. Do we need a monochromatic energy source? Only for XPS, because all of the others are internal transitions, and so our monochromatic information will be lost, or we don't need it. The crime of not having a single energy going in is eliminated by the actual process that we're looking at being an internal energy transfer. Chemical shift is, do we get information on the chemical shift, which, if, for example, can be very important if we've got a hydrogen attached, because we cannot see it any other way. We can only see it as an effect on other elements. That is possible with XPS because we're measuring the energy level of one electron, and it's possible with Auger because we have an odd number of electrons, although it's harder. This is the normal technique for measuring chemical shift. If we want to know, we've got carbon, oxygen, and calcium in there. Is it calcium carbonate or is it something organic with some calcium in? We don't know. If we do X-ray fluorescence, it just tells us what the elements are. We don't know if we do EDX, it just tells us what the elements are, because it doesn't give us chemical shift information. XPS will tell us, but it's a lot harder. So the flip side of having chemical shift information is it's a lot harder to discover unknowns because our peaks move around. Charge ruins. I've written there, that's a bad way of writing it, but if we have charge on there, it will change the spectrum, so we have to deal with any charging of our sample. If we have XPS, we have to deal with it because we need an accurate measurement of the energy of the electrons coming out, otherwise we get no data. X-ray fluorescence, we don't care. An X-ray goes in, X-ray comes out, they're not affected by charging, so it is immune. EDX the same, so paradoxically in an electron microscope, if we allow our sample to charge up, we cannot get a decent image, but we can get an EDX measurement. Auger is obviously critically important because again we're measuring the energies of slow moving electrons, and then we must measure them accurately, otherwise we don't know what we're doing. The next one is how deep does our measurement system penetrate, and that is a combination of how deep does the thing going in penetrate and how deep does the thing coming out manage to escape from. This is again a good and bad thing. So in XPS we have a very low penetration depth. It's of the order of tens of nanometers. So we can get in below the surface, we can measure stuff that aren't just on the surface, but if we take a metal, for example, we will only see metal oxide unless it's got a very thin oxide layer. So it's very low because the electrons coming out don't have the energy to penetrate out. The X-ray can go in as deep as we like, but it doesn't do us any good if the electrons can't get out. X-ray fluorescence has a high penetration depth, which is still only not a few micrometers. So if we take a material, we typically get through the layer of dirt on the outside and can see the bulk material, but different energy X-rays can penetrate out because it's the low energy one coming out. So different energy X-rays can escape from different depths, and there is a critical problem. So if we have something that's not very massive inside our material, so a boron atom for example, we would expect the X-rays that come out that are particularly low in energy not to be able to escape from very deep, and that is the case. So if we have glass where we might want to measure the boron content, or concrete where we might want to measure the boron content, we will struggle to measure very deep, and we will have to make some kind of allowance for the fact that we can measure the heavier elements way deeper inside our material, so our measurement will be biased towards those. The XPS, on the other hand, is biased towards things that tend to accumulate on the surface. So if we take a stainless steel, we will measure too much chromium because it tends to move to the surface. X-ray fluorescence is less susceptible to that because it penetrates deeper. Or better said, the X-rays coming out can escape from deeper. EDX is an intermediate because the electron going in can penetrate further because it's got higher energy than this electron coming out. It's effectively the opposite technique. We've got an X-ray coming out, an electron going in. Here we've got an X-ray going in, an electron coming out. But because the electron has the higher energy, it can penetrate deeper. The X-rays can escape from a higher depth anyway. So we get more deep information, so we have a medium depth. If we take Ogee, problem is again, we need to measure the energy of a low energy electron that's got to escape, and so it's that one that is limiting the depth of our technique. So those techniques, Auger and XPS, are powerful if we want to measure the surface, and X-ray fluorescence, to a lower extent EDX, are powerful if we want to measure the bulk. Those are really handy. Obviously, the ones that measure less chemical information are powerful if we don't know what the sample is, and the ones that measure chemical information are powerful if we need to know what they're attached to. If we have a good idea about what the chemical is that we're using, they are better because they tell us more information, but we can't extract that from the depth. So then we need to do something to make sure that we're measuring bulk material if we need to measure that. The other way round, of course, if we want to measure the general chemical information, but at the surface, we then have a different problem, and so we would have to measure at a lower angle to try to reduce the depth of penetration. We can also do that with X-ray photoelectron spectroscopy. If we rotate our detector to a lower angle, particularly the detector, because that's the thing that's got the lower energy, the electrons coming out. If we look at electrons that come out at a lower angle, we will get them from a lower depth. If we look at them from a higher angle, they will be able to escape from deeper in our material. So we can change it to a certain extent, but we are limited by the physics of the technique. How are we going to measure the energy of the electrons? Well, we can borrow a technique from mass spectroscopy, another technique, but it's not spectroscopy. It's not electromagnetic energy that we're using. Here, we're trying to measure an electron, which is also not electromagnetic energy, so we can use the same technique. It has mass and charge, and it's moving in this direction. So if we apply an electric field, we can bend its path, and it depends on the strength of the electric field how much it gets bent. So if we set up a bent path to our detector, then we can vary this field and select which electrons can get through. It's effectively a filter for all electrons that don't have the correct velocity, because if they don't, they will hit this plate if they're going too fast, or this plate if they're going too slow. So we can have a bent detector. Typically these would be in the shape of half a dome, so that we can gather as many electrons going in different directions as possible, but different geometries exist. Then we can measure the energy by selecting or by sweeping the voltage on this. We could also do it with a magnetic field, but typically it's done with an electric field. We have already seen the fundamental principle of our electron detector, that if we hit an atom, a reasonably heavy atom, with an electron, we can shoot out an electron from it, but the electron that we shot in carries on. So if we set up a suitable optics, electron optics, we can make the two electrons go to our detector, so effectively we've generated a multiplier. If we have enough of these atoms, we can make more. This is the principle that is used to view images in our electron microscope. It's these electrons that we actually measure, the ones that you knock out of the sample. They're called secondary electrons. These are the primary ones. In our detector, we're just trying to get more signal because we will have a small number of electrons and we need to count a lot of electrons to give us a current. So we need to multiply them up. We do that as I drew before, with a set of plates that where the electron hits, more electrons come off and the original one, and they're attracted to a second plate which is also the same. Typically they'll be coated with gold because it has a high secondary electron coefficient, so the number of electrons that come off is quite high, and the gold will be attached to a power supply to give it the electrons back so that it's ready to receive the next electron. It also allows us to control the voltage on all of these so that they're staged, so that each one gives electrons to the next one. Typically they're curved, so it behaves like an optical system. They focus and it goes eventually to a collector that measures the current. There are several types of X-ray detector, but we'll talk first of all about this one, which is a type of semiconductor. The X-ray comes in, it knocks out a number of electrons dependent on its energy. Just check my sound. Yeah. It knocks out a certain number of electrons dependent on its energy. So the accuracy of our detector depends on the band gap, and we try to make it as small as possible. But there's a problem, obviously, because if we make it too small, we will get too much noise from the thermal electrons being knocked up. We attach it to a positive and negative ends of a power supply and measure the current. And so if a photon comes in, we get a spike of current, and we can use that to determine what the energy of the X-ray was. There is a problem, of course. If two X-rays come along at once, we might measure double the current and think it was one X-ray with twice the energy. And so these can only measure up to a certain rate. There is a computer behind it which rejects apparent double events. So if it takes too long, then the second photon came in before the current from the first one was going out. So there is a limit to the physical size of these, and there's a limit to the speed that they can count at. It makes it handy for electron microscopy because not very many X-rays come out. These are comparatively cheap detectors because you only need one detector and you can measure all energies, although the steps are determined by the height of this band gap. There are better technologies if we need to know the energy to a higher accuracy, but those are really expensive, so they would be much more like the detectors and the measurement systems inside an X-ray UV visible spectrometer. So there would be a diffraction grating in there, and because it's an X-ray, it would have to be a bent crystal. Those are expensive. And then we would have a whole range of detectors to measure them. Then the detectors don't matter as much because we have already split the wavelength up. So we can use the same type of detector, but we're only looking for number of photons because we know what the energy is at that position. That's obviously really handy. We could use any old detector. A camera detector will detect an X-ray. But what we can't do so easily is split up the energies. That's the bit that costs money. So as you can see, these type of techniques involve the core electrons of atoms, and they tell us more about which elements we're looking at, but they do tell us information about which elements they're connected to, if we use the right ones. It's a family of techniques that all use the same physics, and they are logically connected. But now we're outside the range where we're talking to the bond, and so less chemistry happens, so it's less to do with actual chemistry. However, they're very useful techniques and much more used in material science, because if we want to measure a metal, infrared is fairly useless. This is much better for infrared because it doesn't get affected by the conduction of the material. It's much better in composite materials because we have better penetration and we're looking at all of the elements in there. Graphite, for example, is difficult to measure with infrared. It does have a Raman signal. So these techniques have their place. We typically don't go up any further in energy than this because then we're talking to the nucleus. There is another technique, NMR, that uses the nucleus, although it uses actually radio frequency energy. It uses a lot lower energy, but we are not going to manage to get there in this course. So we're going to stick here because gamma is not so important to chemistry. So let's stop there. That's another set of techniques for you, and we will continue next time.